solve a numerical problem related to first order systems in series, related to the dynamics of two first order systems in series. So this numerical is an exercise question from the textbook Process Systems Analysis and Control. The textbook titled as Process Systems Analysis and Control, authored by Donald R. Kaufnor, Dr. Kaufnor. So this is an exercise question taken from that book. When we solve this problem, we will understand the concept of first order systems, two first order systems in series, the dynamics, and the nature of the response. Well, the question is this: two non-interacting tanks are operating in series with a steady flow rate of 20 feet cube per minute. At time t equal to 0, 10 feet cube of water are quickly added to the first tank. Question number 1, determine the response in the level of both tanks. There is another question: determine the maximum deviation in level in both tanks from the ultimate steady state values and the time at which each maximum occurs. There is some data given. A1 equal to A2 equal to 10 feet square. A1 and A2 are the areas of the two tanks. R1 resistance of the first tank 0.1 feet per CFM. CFM stands for cubic feet per minute. CFM is cubic feet per minute. It is the same as this. It is the same as this, feet cube per minute. CFM and foot cube per minute are one and the same. CFM is same as foot cube per minute. Okay. R2, the resistance of the second tank is 0.35 feet per CFM. Now, two non-interacting tanks. Let's go to the solution. Two non-interacting tanks. If you look at the figure, two non-interacting tanks with the usual notations. This is inlet flow rate Q, height in the first tank H1, resistance of the first tank R1, Q1, outflow from the first tank, which is the inflow to the second tank. This is second tank. This is second tank. This is first tank. R2, resistance of the second tank. Q2 is the outflow from the second tank. Now let us take tank 1. First consider tank 1. Tank 1 transfer function H1S by QS. H1S by QS is this. H1S by QS, we know. Transfer function of single tank, first tank, is R1 by tau 1S plus 1. And it is also given here, they are operating at steady state with the flow rate of 20 feet cube per minute. So at steady state, this flow rate Q and this flow rate Q1 and this flow rate Q2, all the three flow rates will be equal at steady state. At the initial steady state, all the three flow rates are equal. So that is what is this: QS equal to Q1S, QS equal to Q1S equal to Q2S. All three are equal to 20 foot cube per minute, 20 CFM, right? Now what sort of input is given? At t equal to 0, 10 feet cube. Foot cube is a unit, volumetric unit of water quickly added to the first tank. Suddenly you add 20 feet cube, sorry, 10 feet cube, quickly added to the first tank. So for momentarily, instantaneously. So at that instant, the flow rate is going to quickly suddenly change from 20 to higher value and come back to the original value almost instantaneously because it is quickly added. So at t equal to 0, the flow rate, inlet flow rate, this is going to change momentarily, quickly from 20 to higher value and then quickly come back to the original value once addition is over. So this is an impulse input. This is an impulse input. So what is impulse input? The details of impulse input are discussed in my lecture video titled as PC23. So this is the impulse input, which how it is written: impulse input Q of t, this Q of t in terms of deviation variable, capital Q is the deviation variable, equal to m into del t. And what is m? M is how much water is added quickly? 10. M is 10. M is 10 feet cube. M is 10 feet cube. Now let us find the response H1. So by the usual method, take Laplace transform. Q of S equal to, take Laplace transform. Qs equal to Laplace transform del t is 1, so m. Qs is equal to m. And if you substitute this Q of s here, H1s equal to H1 is equal to Qs into R1 by tau 1s plus 1. So that is what Qs into this. Now for Q of s equal to m, so substituted m here. So m r1 by tau 1s plus 1. Next, if you take L inverse Laplace, H1 you will get H1t. So what is the inverse Laplace of this? M r1 by tau 1s plus 1. Inverse Laplace of an impulse function is this. So H1t equal to M r1. M r1 is a constant. So 1 by tau s plus 1. Inverse is 1 by tau e power minus t by tau 1. This must be tau 1. This should be tau 1. So the inverse of this is e power minus t by tau 1 divided by tau 1. So this has been, in case you don't remember this, in case you want to know how we got this, you can refer to my lecture titled as PC16, which is available in this channel. The link for this is given in the description as well as above. So the inverse of this is this. Now all we have to do is you have to simplify this equation, substituting the constants tau 1, r1, m, etc. Now what is tau 1? Tau 1 is, for tank, tau is equal to A into R. So tau 1 is A1 into R1. A1 is 10. R1 is resistance 0.1 given in the data. So tau 1 equal to 10 into 0.1, 1 minute. So let me substitute these values here. We substitute H1t equal to M is 10, R1 is 0.1, and tau 1 is 1, e power minus t, tau 1 is 1. So this is the equation for H1t. Now, what is capital H1? Capital H1 is the deviation variable, H1 minus H1s. So H1 minus H1s equal to e power minus t. Now, if you want to know this, find out, calculate H1, you have to evaluate this constant also, H1s. So how do you get H1s? To find H1s, we go to the flow head relationship. So which will assume to be linear here. We will assume a simple relationship for flow head. So assuming that flow head relationship to be linear, so you know this is a linear relationship for the flow head. Q equal to H by R. So Q1 at steady state equal to H1s by R1, right? So from this you can calculate H1s. H1s equal to Q1s into R1. Q1s steady state value is 20. We have taken Q is given in the question. Q1s is 20. R1 is 0.1, so 2. So if I substitute this H1s here, and I can write H1. So H1 equal to, so when I substitute H1s in this equation, I take an H1s to the other side, 2. This is H1s, this is H1s. I take it to the other side, plus E minus T. So this is the equation for the response in the level of the first tank. So how does the level in the first tank vary with time after the tank has been given a disturbance in the form of an impulse input? The level in the first tank is going to vary by this equation, H1 equal to 2 plus e power minus t. So if you want to know what will be the height at any time after the disturbance, you can calculate from this equation. For example, if you want to know what will be the height of the first level in the first tank at t equal to 2 minute, all you have to do is substitute t equal to 2 minute here and calculate the value of h. So this is the response in the level of the first tank after the disturbance, right? So what is asked is determine the response in level of both tanks. We have found out for tank 1. So that is this. Now let us go to tank 2. So tank 2, if you want to find out the response in the level of tank 2, H2. So we have to relate H2 and Q. So this becomes two first order systems in series. So when you have two non-interacting first order systems in series, the overall transfer function will be what? Will be the product of the individual transfer functions. Will be the product of the two individual transfer functions. So H2S by QS will be equal to Q1 by Q into H2 by Q1. This is for the tank 2, product of these two transfer functions. So this is H2 by Q equal to Q1 by Q, H2 by Q1. So these have been discussed in detail. How do you write the overall transfer function for two first order systems in series? If it is non-interacting, it will be equal to the overall transfer function will be equal to the product of the individual transfer functions. So this has been discussed in PC2. My lecture titled as PC2 available in this channel. Well, so now let us substitute Q1S by QS, these two transfer functions. If you substitute, what is Q1? Q1 by Q. So Q1 by Q is simply 1 by tau 1S plus 1. So this transfer function Q1 by Q is 1 by tau 1S plus 1. And this transfer function is R by tau 2S plus 1. Okay. H2 by QS is this. H2 by Q1S is R by tau 2S plus 1. Tank transfer function. And the transfer function of first tank transfer function Q1 by Q is 1 by tau 1S plus 1. So the overall transfer function is the product of these two functions. Now the input disturbance is same. The input is same. The disturbance is the same. Disturbance is given to at the inlet of the first tank. So the disturbance given here affects H1 as well as H2. Same disturbance, impulse input. Same impulse input affects both H1 and H2. So the input for the second tank is also the same input, M into del T. Same impulse input of magnitude 10. So let us find out what will be H2T, the response. So take in Laplace Q of S equal to M. And if you substitute in this, H2S equal to, what will be H2S? H2S will be QS into this, right? If the QS goes this side, H2S will be QS into this. So that is what is written here. QS is M. I substituted QS is directly M. So H2S will be equal to M into R by, this must be R2. Okay. So this is R2. Please note the correction. This is R2, not R. Second tank resistance, R2. So this is R2. So H2S, if I substitute here, H2S will be QS into this. QS is M. So MR2 by tau 1S plus 1 into tau 2S plus 1. Now the inverse, L inverse. If you take L inverse, you get H2T. And what is the L inverse of this? This function is a constant. So 1 by tau 1S plus 1 into 1 by tau 1S plus 1 into tau 2S plus 1. Inverse of this is this. So this has been derived in my lecture titled as PC17. So this inverse has been derived. This formula has been derived in PC17. So this term 1 by tau 1 minus tau 2 into e power minus t by tau 1 minus e power minus t by tau 2 is the inverse of this function 1 by tau 1s plus 1 into tau 2s plus 1. Well, so this is the response in terms of deviation variable for the second tank after after the impulse input is given. This is a response in terms of deviation variable. Now let's get the response in terms of the actual level, small h2. Remember, capital letters represent the deviation variables. Okay, let us substitute the constants. Tau 1, it is 1, already you found out. And similarly, tau 2, what will be tau 2? Tau 2 is going to be, what will be tau 2? So tau 2 is also going to be A2 into R2, right? So tau 2 is A2 into R2, right? So A2 is how much? A2 is 10, R2 is 3.5. sorry, R2 is 0.35. R2 is 0.35. 5 to A to R2 equal to 10 into 0.35, 3.5 minutes. So tau 2 is 3.5 minutes, 3.5. This is point, this is 3.5 minutes. So let me substitute all these values in this equation. So H2T equal to m, this is m. So this is m, this is R2, this is R2 by tau 1 minus tau 2. Tau 1 is 1, tau 2 is 3.5, e power minus t by tau 1 minus e power minus t by tau 2. This is tau 2 3.5. I had just substituted the constants into these equations. R2 is 0.35, m is 10, and so on. M 10, R2, t by tau 1, t by tau 2. Tau 2 is 3.5. This is tau 1 minus tau 2. So let me simplify this. If you simplify this, this is going to be 3.5 minus divided by minus 2.5 and so on. So on this deviation variable, this is capital H2T, right? So this is H2 deviation variable. This is deviation variable. This deviation variable H2T equal to this. So H2T deviation variable is what? Small h2, the actual height minus the steady state height, H2S. So equal to this. Now what will be H2S? Again, you go to the flow head relationship, assuming to be linear. So Q2 equal to H2 by R2. At steady state value, Q2S equal to H2S by R2. So H2S is going to be R2. R2 is 20 into, sorry, R2 is 0.35 into Q2S 20. So H2S is going to be Q2S into R2, 20 into 0.35, that is equal to 7 feet. This is feet. Height is 7 feet. So this is feet. Heights are all in feet. You will get heights in feet. Height will get in feet. This is feet. 7 feet. So that's all. Substitute here in this equation. Substitute here for H2S is, for H2S I'm going to substitute 7 and I taken it to the other side. So H2 equal to H2S plus this. So H2 equal to H2S 7 and this is going to be minus 1.4 e power minus t into e power minus t by 3.5. So this is the response in the level of second tank. Okay, this is the response in the level of second tank. So this is a response in the level of the second tank. How does the liquid height in the second tank vary with time? If you want to know what will be the height at any particular instant, we can find out from this equation. For example, if you want to know what will be the liquid height in the second tank at 2 minutes after the disturbance is given, you can find out from this equation by substituting t equal to 2. So this equation gives height as a function of time after the input is given. So in other words, so this is the response in the response of the second tank. To be more specific, this is a response of the level in the second tank, dynamic response of the level in the second tank. So we had found out the response in the level of each tank. H1 we have found out earlier. We have found out H1 here. H1, this is H1. Okay, so this is H1, first tank. This is all in feet. You'll get answer in feet. Okay, you'll get the answer in feet. You'll get the answer in H1 all in. If we calculate, you have to substitute t in minute. So in this equation, t should be in minute and h will be in feet. We'll get h in feet. So substitute t in minute and h is h1 in feet. Same thing here. This also will give you, because you are using consistent units. So this 7 is feet. So this also, this h2 will be in feet. So that is the answer for the first part of the question. First part of the question is determine the response in the level of both tanks. So there is also another part, second part, that is this. So that will be done in the next lecture. That will be done in the next lecture. So please stand by for the next lecture where we'll be solving the second part of this question. Okay, we'll be solving the second part of the question in my next lecture or in the subsequent lecture. See you till then. Bye.